I'm Hajime Asama from the University of Tokyo. First of all, I'd like to thank Wolfram and organizing committee member of ICRA 2020 for inviting me as a keynote speaker. I hope you are all fine in such a very difficult situation of COVID-19 pandemic. In this talk, I'd like to discuss on robot technology for super resilience, including applications of remotely operated robot technology for response to disasters, accidents, and such pandemic. We are constantly exposed to various threats, such as disasters that we have never experienced. By use of technology, we have made efforts to implement a safer and more secure society. Nevertheless, once a new disaster occurs, it claims many victims. Therefore, we should continuously discuss how to respond to the disasters and how to realize a disaster-resistant society. There are various approaches, such as disaster response, which becomes necessary when it occurs, the disaster mitigation to reduce damage to the disaster, and the disaster prevention. However, since disasters are inevitable, it is necessary to consider how to incorporate resilience into our society. That is, the function of immediate recovering after the disasters. Moreover, it is important not to recover to the original state as before the disaster, but also to evolve into a more robust and advanced state than before through the experience of the disaster. I call this ability super resilience. First of all, I'd like to define robot technology. This word was defined by METI, Ministry of Economy, Trade and Industry of Japan, as technology that includes sensing system, intelligent control system, and driving system. RT is created in contrast to ICT, which is technology on information and processing and communication in information or virtual world. RT is a synthetic technology on detection, measurement, recognition, control, motion, task in physical or real world. So the important point of RT is that it is solution derivation to the social problems and needs by synthesis, especially system integration according to the requirements. This is a robot called Quince, and this robot was used for the decommissioning mission of Fukushima Daiichi nuclear power plant accident. And given the requirements and the environmental conditions, they designed and developed this kind of very specialized system. And this is typical example of RT. In Japan, there are various types of the disasters, such as earthquake, tsunami, volcano explosion, fire, typhoon, flood, and landslide. And we have also various types of the accident of artifacts, nuclear power station accident, and also accident of social infrastructure such as tunnels, bridges, and so on. And now we have pandemic disasters. But the disasters are very diverse. For example, in case of Great Kanto earthquake, which happened in 1923, most of the people are killed by fire. But in case of Great Hanshin Awaji earthquake, which happened in 1995, most of the people are killed by collapse of the buildings. And in case of Great Eastern Japan earthquake, which happened in 2011, most of the people are killed by tsunami. So when we consider the RT required to the disaster response, it quite depends on the type of the disasters. So we need some kind of portfolio of robot technology for disaster prevention and response. For example, aerial vehicles and ground vehicles, and also underwater vehicles. And the disaster response robot required is quite changing depending on the operation phases. Just after the disasters, needs of the RT are information collection and investigation and evacuation guidance. But until 3 days, the needs for RTs are fire extinguishing and search and rescue. After that, needs for RT will be changed to recovery and also reconstruction. There are other needs, for example, inspection and monitoring. This is a needs for preventing the disasters. Now I'd like to introduce what happened in the case of Great Eastern Japan earthquake. It happened in 2011 and the magnitude was 9.0. This is a seismic center. And the huge tsunami happened 30 or 60 minutes later than the earthquake. And it attacked the east coast area of Japan and it destroyed completely this area. And more than 15,000 people are killed by this tsunami. But another biggest issue was the accident of Fukushima Daiichi nuclear power station. This is the location of the power station, and it is very close to the seismic center. And this is a scenario how this accident happened. The scrum was successfully done. But after that, all the fuel tanks and generators were damaged by the tsunami, and station blackout happened. Then cooling system and reactors and fuel storage pool became inferior, and cooling water was lost. And then the meltdown of nuclear field happened. And the hydrogen explosion happened in 3 units, and huge amount of contaminated material scattered in the environment. This is a kind of picture which was taken from the air just after the accident. So unit 1, 3, 4, the reactor buildings are totally damaged by the hydrogen explosions. Unit 1, 2, 3 were under operation when the accident happened. So all the nuclear fuels which was inside of the reactors were melted down. And the final mission of decommissioning is to retrieve all the melted down fuels, which is called fuel debris, and also the fuels stored in spent fuel pool. This is mid and long-term roadmap summary, which was issued by TEPCO company. And they said it will take more than 30 years, 30 or 40 years for final decommissioning. Now we are at the end of phase 2. So we should immediately start the fuel debris removal. So it is quite long-term mission. And the needs for remote technologies are everywhere because the inside of the reactor buildings, most of the environment are so much radioactive, highly contaminated. And these are the needs or tasks for remote technology. Water injection, removal and transportation of rubble, fuels, and contaminated water, investigation, measurement and mapping, sampling, decontamination and shielding, fixing and contaminated water leakages, handling, transportation, removal, setup of devices, instruments, equipment, and so on, and waste and contaminated water management, and dismantling and facilities. Now, I'd like to introduce some example robot technologies which were used already in the decommissioning missions. This is remotely controlled unmanned construction system, which was used for rubble cleanup. Just after the accident, there were lots of rubbles, highly radioactive rubbles in the site. And they decided to introduce this kind of unmanned construction systems to remove, clean up all the rubbles. All the machines are remotely controlled. And the mission was very successful, and all the highly radioactive rubbles were removed by this kind of systems. And this is another story. This is the Queens, as I mentioned before. So this was used for various missions, and it was also used for investigation inside of reactor buildings for Unit 2. It was very successful, but on the way back, it was stuck at the third floor. And in addition, there are many types of robot developed for investigation inside PCV. It is primary containment vessels. So fuel debris is considered to exist inside of this area, which is called pedestal. But this area is covered by very thick concrete. The only way to insert the robot is through the pipe, which is called penetrations. So this is transformer robot, which was introduced into the Unit 1. And this is Scorpion type robot and also telescopic type of robot, camera and grippers, which was used for Unit 2. In case of Unit 3, they developed this kind of very small ROV, and it was inserted to the Unit 3. And the mission was very successful. Today, I have not so much time to introduce all the devices which was used in this Fukushima Daiichi nuclear power station. But as far as I know, more than 50 kinds of robot technologies were already used. Most of the missions are very successful, but still some are in failure. So we should analyze what are the failure and what are the factors of failures. So factors of failures are divided into two types, direct factors and indirect factors. For direct factors, main factors for failure is communication loss and misoperation of operators and malfunction by radiation. Indirect factors, it is because most of the robot systems are developed as a prototype system. They are not the products, so they are not so reliable. And also another factor is that the environment was not known when it was designed. So it is really a difficult mission to design and develop and introduce this kind of robot system to that disaster site. And in the site, they want a remote teleoperated RT system. They don't want any autonomous robot because it is impossible to do the missions. So we need distributed system technologies and human interface and communication to construct the teleoperation system. But to facilitate the teleoperation, it is very important to consider situation awareness and also autonomy and also some psychological aspect such as body consciousness. Now I'd like to discuss a little bit about the COVID-19. Of course, there are lots of needs for RT for response to COVID-19. So we should avoid three C's, which are closed space and crowded spaces and close contact setting. And we should reduce contacts for infection prevention. So we discussed a lot about what are the needs of the robots and the IoT applications for pandemic disasters. These are some examples. Disaster response activities, prevention of outbreak, robots for prevention, countermeasures, and recovery of pandemic disasters, robots equipped with real-time PCR, indoor robots equipped with alcohol spray, surveillance and temperature detection robots, on-site triage utilization IoT, autonomous driving ambulance, communication transportation robot, robots for handling contaminated materials, decontamination of robots, evaluation and policy making and safety, prediction of contaminations. And for the disaster response activities, prevention of infection of medical or healthcare personnel, robots in reception, consultation, nursing, inspection, and treatment for minimization of contact of infected persons, remote monitoring of those during home quarantines, avatar robots for understanding and the biological condition of the infected person and for consulting data collection and advanced diagnosis, lift and nursing robots for substituting physical contact and for the elderly and dementia, robots for communication and walking support with VR or AR, autonomous cleaning robots, robot infrastructures, and real-time measurement of infected persons, and the biometric information collection for aggravation prevention. And we should discuss about needs for robot technology in disaster response in aspects of information support and physical support or psychological support. Now, we should discuss about technology development, but we need also to discuss about technology disseminations. So robot systems should be incorporated to the resilient facilities or cities or society. So smart cities should have some kind of robot technology. Robot technology should be embedded to the smart cities for super resilience. It should be human cause existing robot technology, including IoT and IOR, Internet of Robots, and the Internet of Humans. So we discussed a lot how to promote the dissemination of robot technologies for disaster response, projects and programs for RT system R&D, and also RT testing facility for disaster prevention and response, and strategy planning, standardization, and regulation design. So based on this kind of proposals, Japanese government established some projects such as SIP. And in this program, there was a project which is for infrastructure maintenance and renovation and management. There are some projects for research and development on robotics technologies. And these kind of new technologies were developed and utilized for the infrastructure systems. Another program is called IMPACT, Impulsing Paradigm Change Through Disruptive Technologies. And one of the project is called Tough Robotics Challenge. In this project, they discuss tough robotics, and these kind of new robot technologies were developed for disaster response. And some new competition was also designed, which is called World Robot Summit. So originally it was planned to be held in 2020, but due to the COVID-19, it was postponed to 2021. So in these competitions, there are some categories: industry robotics, service robotics, and disaster robotics. So I hope if you are interested in this kind of competition, you join this challenge. So finally, I'd like to summarize my talk. I discussed super resilience. It is adaptation and evolution by multiple feedback loop based on experience, and also the design of resilient systems, facilities, cities, and society, which includes the robot systems, robot technology embedded the smart cities. And finally, I'd like to point it out that human viewpoint is very, very important. It is not so economical, but it is very important to protect the humans. And also, it is very important to cooperate internationally to utilize this kind of robot technology and also disseminate the technology. Okay, thank you very much for your attention.